Assalamu alaikum. Welcome back. So in this session, we will be talking about the unsteady flow processes, right? So till now, we have been dealing with steady flow processes, which are extremely common in a lot of practical applications of interest. However, a lot of applications are also unsteady. And so today we'll be talking about how do we apply the energy balance for unsteady flow processes, how do we deal with them, and how do we calculate the heat, work, or whatever is related for such sort of unsteady flow processes. Okay, so now let us define what we mean by unsteady flow process. So unsteady flow processes are processes which involve changes within the control volume with time, meaning properties within the control volume are going to change over time. It could be that the mass is changing with time. It could be that the volume is changing with time. It's just that they're not constant, right? If you measure something now versus measuring the mass maybe after 10 minutes is going to be different. So also all processes where things or quantities within the control volume, they change over time. These are called as unsteady flow processes or transient flow processes, both of which mean the same thing. Things are changing with time, right? So there are a lot of common examples. One example could be charging or discharging of a rigid vessel, right? Another example that's more closer to home could be inflating a tire or a balloon, or basically you could also think about a puncture of a tire or a balloon, right? In both of these situations, the mass or the volume of air within the tire or the balloon is either increasing when you're filling the air within the balloon or the tire, or in case of a puncture, the mass of the air and the volume of the tire, both of them are decreasing with time when the puncture happens. So these are situations, and a lot more, of course, are situations where we are having quantities within the control volume which are changing with time, right? Which makes these processes unsteady. Another example could be something that we see here on the slide. This is an example of an unsteady flow process where things are changing with time, the properties within the control volume. So this is our control volume, right? And this is the control volume shown by the dotted line, and the properties within the control volume are changing with time. Maybe the energy is changing with time. So we provide some heat input in here through the electrical work. We provide some rotating shaft input. Maybe there's some heat transfer happening, and there is some mass coming into the system, right? While all of this is happening, the mass within the control volume is keeping on increasing because there's just one inlet, but there is no outlet, right? So this is another situation where the the properties within the control volume are changing with time. There are, of course, a lot more other examples, and you can also think about some more examples that you see around yourself where things are changing with time. And for all these processes, we need to go back to the energy equation and look at how we can solve. Okay, so all of these uh, uh, processes, which are unsteady flow processes, because things within the control volume change with time, can be represented well with a uniform flow process. So we make some sort of a simplifying assumption here when we are going to deal with unsteady flow process. So the assumption is that we're going to treat these as uniform flow process. So essentially what we are saying is these are unsteady, unsteady state, uniform flow processes, right? So now the question is, what is uniform flow? So when we say the flow is uniform, what we are saying is that the fluid flow, right, gas or liquid, at any inlet or at any exit is uniform and steady. Okay, there are two things here. We're saying it's uniform as well as it's steady. So what do we mean by uniform? By uniform, we mean that the fluid properties within at the inlet or the exit are not going to change with position, or they're not going to change over the cross section of the inlet. So at any point on this inlet, right, at this point, or this point, the properties are exactly the same. They're not a function of the position within the inlet. It's a simplifying assumption. It does not depend on the position on the inlet. Same way, we are also saying that the properties at the inlet or the exit, they're not going to change with time, which means they're steady. Okay, so if any of them change with time or with position, we're going to take an average value. Essentially, what we're going to do is we're going to treat the inlet and the exit as constants, right? Remember, the inlet or the exit, the properties we're going to treat them as uniform, right? So constant in position and time. but it does not mean that if they are constant, then the properties within the control volume are constant. For example, if you are constantly filling the balloon at a fixed mass flow rate, the mass of the balloon is changing, right? So the mass, the properties within the control volume are changing. So it is still, the balloon as a whole is unsteady, but it is having uniform flow. The flow coming into the system is constant. It's constant over position and it's constant over time. So steady meaning constant over time, uniform meaning constant over position. So this is a simplifying assumption for inlets and exits only. Within the control volume, of course, things are unsteady and they change over time. Okay. So now when we talk about unsteady flow processes, in addition to assuming that the flow is uniform, we tend to make some more assumptions in terms of how are we going to deal with it. So first thing is, when we talk about unsteady flow processes, we're always going to deal with unsteady flow processes over a given time duration. So you're going to talk about, okay, at time 0, the balloon has volume 0.1 meter cube, and at time 30 seconds, it has a volume of 0.3 meter cube, right? So you're talking about fixed duration of time over which things are happening. Okay, you're not just talking randomly. So we fix the time duration. And again, if we fix the time duration, then the amount of change that happen is not dependent on the rate, right? I mean, it of course depends on how quickly or how slowly it's happening. That's going to define how much change happened. But of course, here, since we are fixing the time duration, we are not so focused on writing an energy balance or the mass balance in terms of the rates. We are interested in quantifying how much change happened, right? So the way we treat it is very much like a closed system where we were interested in quantities, but not the rates. We were interested in what is the mass at the inlet, mass at the exit. We are not interested in the mass flow rates. Okay, so we treat it as the closed system, but with of course inlets and outlets, which makes it an open system, of course. So it is like a closed system. It is not a closed system because there has to be an inlet or there has to be an outlet. Or if you have both inlet and outlets, the flow rates through both of them should be different so that things change within the control volume. Okay. Now, when you think about the mass balance, there are two things that are happening. Okay, so let's just again maybe think of the balloon as an example, right? So mass coming into the system, right, minus mass going out of the system should be equal to change in mass within the control volume, okay? Or it should be equal to mass at state 2 of the control volume minus mass at state 1 of the control volume. So these are, you got to be careful with this because these are two very different quantities. Here we are talking about the mass coming in, okay? And here we're talking about the mass of the control volume. So it's like the mass of the balloon here, all right? Whereas this is simply the mass of air that is coming in. Okay, so basically what we are saying is, let's say if you're just filling the balloon, so there is some amount of mass that's going to come in, and it's going to come in, it's going to come in at a steady number, and there's, let's say there's no mass outlet because of course you're just filling the balloon, so mass out is 0. So in that case, mass in should be equal to m2, which is the mass of the balloon at state 2 after a certain time, minus mass 1, which is the initial mass of the balloon. And this is what you would expect, right? If you start with the mass 1 of the balloon and you start filling it with air and you fill a certain amount of mass mn of the air, then of course the balloon will be at mass 2, where mass 2 is simply m1 plus mn. Or you could say that m2 minus m1 is equal to the mass of air that went in. This is as simple as that. Okay, so you're just saying that the mass at the inlet minus mass at the outlet should be equal to the change in mass of the control volume. All right. So if let's say you don't have any inlet, mass inlet is 0. If you do not have any outlet, mass outlet is 0. And if the system that you're dealing with is initially evacuated, right? If it has nothing within, if there's vacuum within the system, then the mass of the system of the control volume at its initial state or state 1 is 0. Okay. So if the system is evacuated, mass in or mass out are not 0. It's mass 1 which is 0. All right. So these are two different things. We're talking about mass or energy of the control volume and mass at inlet and mass at exit. Okay. And of course, they are all related. They're related by the simple mass balance equation that we have written here. And we are not interested in the rates because we know for sure the over what duration we are talking about. So we're just talking about the quantities, right? We're talking about kilogram, no kilogram per second. So in general, we can say that we can have multiple inlets, multiple exits. So the mass coming in from all inlets minus the mass going out from all exits should be equal to the change in mass of the control volume, which is M2 minus M1 of the control volume. This is simply what we have. Same way, just like we have written the mass balance, we can write the energy balance. So energy balance can be written as Qn minus workout, and these are the energy transfer quantities, plus the mass coming in through all the inlets, mass times the associated energy, which is enthalpy plus kinetic plus potential energy, minus the same thing that's going out, should be equal to the change in energy of the control volume. Now, when we talk about the control volume itself, it is simply uh, energy of the control volume at state 2 minus energy of the control volume at state 1. Or if you want to talk about specific energy, we can write it as mass times the energy at state 2 minus mass times the energy at state 1 for the control volume. Okay, here the theta simply refers to the terms that go into the equation when we're dealing with an open system or when we're dealing with flow quantity. So that's enthalpy plus kinetic energy plus potential energy. Just like we dealt with these things for an open steady state open system. So these are the things which are related to inlets and exits. Okay, these are the things which are related to the inlets and outlets of system. On the other hand, till now, for steady state systems, we were considering delta E to be zero, but now for unsteady, it's not zero. And the change in energy of within the control volume is not equal to enthalpy. It's basically equal to the internal energy, which we always take, plus the potential, plus the kinetic energy, plus potential energy. Okay, so this is really, really important here. The enthalpy that we have here is associated with flow work. So it's U plus PV, right? It's associated with flow work, PV flow work, which is happening. But when you talk about the control volume as a whole has a given properties. It does not, there's no flow into the system, right? I mean, the quantity of air or quantity of any substance within the system, within the control volume has fixed properties. So the flow that's coming in and going out is taken care in terms of this energy balance. But the energy as a whole for the control volume, it's given by internal energy plus kinetic plus potential energy, right? So this is an important distinction. Previously, we would consider the changes in internal energy, the changes within the control volume to be zero. So we did not consider this for steady state, but for unsteady, of course, there are changes and we need to consider it. And you got to be really, really clear where you got to take enthalpy, which is happening only in case of when you're dealing with flow, which is happening at inlet and exits, and internal energy, which you're dealing with, which is what you take when you're dealing with the control volume. Okay. Now, in general, we can go ahead and assume that the changes in kinetic energy and the potential energy are negligible for the incoming and the outgoing mass as well as for the control volume, which basically means that the above equation gets simplified and we can write Qn minus work out plus summation of all the inlets times mass times enthalpy minus same way summation of all the outlets times mass times enthalpy should be equal to M2 U2 minus M1 U1 CV, right? We're saying that the only energy which is changing within the control volume is the internal energy because the contribution of kinetic energy and potential energy is very small, right? And this is what we have seen before. In most cases, the contribution of kinetic and potential energy is really, really small. So even if you just have one inlet and no exit, the contribution of kinetic energy is so small that, you know, even if you neglect it, it's not going to change the situation too much. Okay. This is best understood by solving problems. So we're going to solve two problems, one today in this session, and the other problem I'll solve it in the class so that we can take more questions directly and try to understand any concerns or questions that you have. Okay, so now let's look at the first question that we're solving. So here we have been provided a 0.12 meter cube rigid tank. Okay, so it's a rigid tank, it's a fixed volume tank, and it contains saturated refrigerant R134A at 800 kilopascal. At this point of time, it does not say it's saturated vapor, mixture, or whatever, right? So we will read the question further and understand it. So it contains refrigerant at 800 kilopascal, and initially at state 1, 25% of the volume of this tank is occupied by a liquid and the rest is occupied by vapor. So when you look at this, what we're saying is we have this tank here, which is of course our control volume. And about 75% of the volume of the tank, meaning 0.75%, 0.75 into 0.12 meter cube, is filled with vapor or saturated vapor. And the remaining 0.25 into 0.12 meter cube, 25% of the tank, of the volume of the tank, is filled with saturated liquid. So at state 1, what we have is actually a mixture, right? A saturated mixture. Both liquid and vapor are there. And we know how much volume they're filling. Okay, we have a valve at the bottom, right? So you have a valve at the bottom of the tank, and you open that valve now. So we have one exit, no inlet. All right. So you open this valve, and of course, when you open the valve, the liquid is going to come out, right? So liquid comes out of the tank, and we withdraw liquid from the tank. Now, how much liquid do we withdraw from the tank? Well, we don't know yet. Okay. So heat is transferred to the refrigerant. So we heat up the refrigerant. So there's some heat coming in. There's some heat coming into the refrigerant in such a way that the pressure inside the tank remains the same. So basically what we are doing is we have initially this condition where we have a saturated mixture. Then we open the valve, let the liquid flow, and we sort of let the liquid flow, and at the same time, to maintain pressure within the tank to be 800 kilopascal, we heat up the refrigerant within the tank, or there is some heat input into the tank that is happening. Okay, the key point being that the pressure has to remain constant while this process of, withdrawing the liquid from the tank is happening, or while the process of removing the liquid from the tank is happening. Now the valve is then closed when no liquid is left in the tank. So you keep removing the liquid, and when there is absolutely no liquid in the tank, that's exactly when you close it. Okay. Now for this particular situation, we need to determine the total heat transfer for the process. So the question is very simple, right? We need to determine the heat transfer, or we need to determine how much heat we need to transfer to the refrigerant, such that when you remove all the liquid from the tank, the pressure should remain at 800 kilopascal. That's our simple goal. Okay. So now let's write down the information that we have. So we're talking about a certain control volume that we're dealing with, and the system that we're talking about is an open system, of course, because there is mass transfer. Mass is going out from the system, and this is the substance, and there's just one exit, no inlet. Okay, this is what we have. Let's write down the information that we have. At state 1, we have been told that the volume is 0.12 meter cube, the pressure is 800 kilopascal, and the fluid or the saturated liquid fills 25% of the volume of the tank. So the volume of the fluid is equal to 0.25 times V1, or V1 being the volume of the tank. Now, at state 2, what we have been provided is the system undergoes process from state 1 to state 2 in such a way that the pressure is remaining constant at state. And of course, at state 2, we have also ensured that there is absolutely no liquid remaining in the tank. If there's no liquid remaining in the tank, then the quality at state 2 should be 1, because it's all saturated vapor. And this process is unsteady state uniform flow process. Okay, or unsteady uniform unsteady state uniform flow process. This is basically what we're dealing with. Of course, the pressure is remaining constant, which is what we have kept, and we want to determine how much heat we need to transfer to ensure that the pressure actually remains constant. So it's an isobaric process that we're dealing with. Now remember, in addition to state 1 and state 2, we also need to write about what is the state of the substance that is going out, right? In this case, it's just something that's exiting. So what is exiting is simply saturated liquid. So the quality of the substance that is exiting is 0. And it is exiting at pressure 800 kilopascal because, well, that's the pressure inside the tank. Okay, so this is what we have here. Now, there is no mention of the kinetic and the potential energies. So what we're going to do is we're going to make an assumption that the delta Ke and delta Pe are negligible for both the mass, right, that comes and goes out, where here it's just going out, as well as for the control volume. So we don't have to bother about the kinetic and the potential energy when we write the energy balance. Okay, this is a reasonable assumption. This is very much true as we have seen before in the examples that we discussed earlier in this recorded lecture. So now the energy balance would look like this: Qn minus work out plus the summation of all inlets times mass times enthalpy, same way at the outlet, should be equal to the change in energy of the control volume, which is M2U2, U being the small specific internal energy, minus M1U1. Okay, this is what we have. Now let's start simplifying things. There is, of course, no work output happening. So let's cancel out the work. And there's, of course, just a single exit. So we don't need the summation sign. And there is absolutely no inlet. So let's just cancel out all the inlet parts, right? So what we are left with is a rather simplistic energy balance equation where we can write Qn as equal to mass at the exit times enthalpy at the exit, right? Remember, this is just saturated liquid that is exiting the system plus M2 U2 minus M1 U1 of the control volume. How did we get this? Well, we just send this negative MH part to the right. That's how we got it. Very simple. Okay. Now we got to remove as many unknowns as possible, right? So we don't know M1, we don't know M2. There are ways to find them. We don't know U1, we don't know U2, but again, we have some information given that can help us determine them. And we also don't know enthalpy at the exit. But the first thing that we can actually start noting down here or simplifying is basically the mass at the exit. How much is leaving at the exit? Okay. We don't know the number, but what we can do is try to write it in terms of the other quantities, right? Mass M2 and M1. So let's apply the mass balance. Okay. When you talk about the mass balance, well, very simply, we know that the mass that is entering the system minus the mass that is exiting the system should be equal to the change of mass within the control volume, or the mass at state 2 of the control volume minus mass at state 1 of the control volume. Okay. Now, in our case, there's absolutely no mass that's coming in, right? So the mass out, we have written that as mass at exit. So I can say minus ME is equal to M2 minus M1, or ME is equal to M1 minus M2 of the control volume. Okay, so this is what we get from the mass balance, right? So this allows me to actually replace ME and write it in terms of M1 and M2. And that's exactly what we're going to do here. So ME is equal to M1 minus M2. So I'm going to substitute that into this equation right here and rewrite it. So Qn is equal to M1 minus M2 times He plus M2U2 minus M1U. Now let's start writing down the things for all the stuff that we know, right? The easiest thing for now to start off with is enthalpy at the exit. We know that we're dealing with saturated liquid because the question clearly mentions that only liquid was exiting, right? We withdrew all the liquid, okay? So we're dealing with saturated liquid, and also we know the pressure. Pressure is 800 kilopascal. Okay, so then it's really simple. We just need to go to the table for the refrigerant R134A, and enthalpy He would simply be equal to HF at 800 kilopascal because, well, we know saturated liquid, we know the pressure, and that's equal to 93.42 kilojoule per kilogram. Okay, so that's our He, right, obtained right there. Now we also have some information about state 2. At state 2, which is the final state, we have withdrawn all the liquid. So the tank is filled with saturated vapor, right? And we said quality at state 2 is 1, right? Which basically means that we can determine the properties for state 2, or the internal energy for state 2 specifically. So U2 is simply equal to Ug at, again, the pressure, which is 800 kilopascal. So U2 is going to be equal to Ug at 800 kilopascal, which is 243.78. And we get both of these quantities from table A level. Okay, so now we have some information in there. So we have been able to determine, let's say, U2, and also we have been able to determine He. Now we need to go and look at the masses. All right, so let's talk about mass at state 2. Mass at state 2 was in this particular rigid tank. Now here we know the volume of the rigid tank, right? And it's a fixed volume. So we can write the mass as volume divided by the specific volume at state 2. Okay, so now we have enough information at state 2 because we know that at state 2, uh, we have saturated vapor within the tank and we know exactly the pressure, right? So we can simply write this as volume is fixed is 0.12 meter cube divided by V2 would simply be specific volume of saturated vapor, so Vg at 800 kilopascal. Okay, so this would simply be 0.12 divided by 0.0255, 4.706 kilogram. So now by simply reading and understanding the question, we calculated or we were able to calculate mass at state 2, right? So that's extremely helpful. Although we still have some way to go. Okay, so mass at state 2 is known now. Of course, we need some more information and we'll talk about it in a bit. So mass at state 2 comes out to be 4.706. Now, we also need mass at state 1. Sorry, we got mass at state 2. Now the question is mass at state 1. How do we determine mass at state 1? Well, what we know is at state 1, we had some amount of saturated liquid and we had some amount of saturated vapor. The good thing is we know exactly how much volume was being occupied by the vapor and we know exactly how much volume was being occupied by the liquid. So I can say mass at state 1 is mass of saturated liquid plus mass of saturated vapor. Okay, or I could write volume of saturated liquid divided by the volume of saturated liquid at state 1 plus volume of saturated vapor divided by specific volume of saturated vapor at state 1. Okay, we have enough information at state 1. Well, state 1, the pressure is 800 kilopascal again, so we can easily get this information, right? That's simply obtained uh, from the property tables. So the key point here is going to be the volume of the fluid, right? So volume of the fluid, we were told that the saturated liquid fills 25% of the volume. So it's 25.25 times 0.12 meter cube divided by Vf at 800 kilopascal plus 0.75 times 0.12 divided by Vg at 800 kilopascal. Again, from table A11, we can obtain all of these quantities right there. Okay, so once you do that, then basically it is Vf is basically this number in here, right? Vf at 800 kilopascal and Vg would exactly be the same number because we are at the same pressure. So Vg be 0.0255. And we now have the mass of the fluid, saturated liquid and mass of the saturated vapor. So it turns out to be 35.49 kilogram for the saturated liquid, 3.529 for the saturated vapor. And the total mass, of course, at state 1 is going to be 39.02 kilogram. Now remember, we still do not have the quality at state 1. X1 is not known to us yet. Okay, and it is a very common mistake for students to read that, okay, at state 1, saturated liquid fills 25% of the volume and saturated vapor fills 75% of the volume. So the quality is probably 0.75. Well, this is a mistake here because quality is defined in terms of mass. It's not defined in terms of volumes, right? So quality at state 1 is mass of saturated vapor at state 1 divided by the mass of the mixture, which is simply the mass at state 1. So it's going to be 3.529 divided by 39.02, which is what we just obtained here. 3.529 being the mass of the saturated vapor, 39.02 being the mass of the mixture at state 1. And this is going to be 0.0904. Okay, so you can see it's very, very different from 0.75, right? So um, uh, it's really, really important that you remember that quality is defined in terms of the mass and not in terms of the volume, right? So now we have enough information here. We already have the quality, we have the mass at state 1, we have mass at state 2, we have enthalpy at the exit, and we also have the internal energy at state 2. So here you can say we have M1, M2, HE, M2, M1, of course, we have U2 as well. The reason why we found quality is because, well, at state 1, we're dealing with a mixture, and so we need the quality to determine the internal energy at state 1. U1 would simply be UF plus X1 times UFG, right? So we needed the quality, and now we have that quality. So let's go ahead and start substituting the numbers. So UF is 92.75. It's basically UF at 800 kilopascal because that's the pressure we know, plus X1 0.0904 times UG minus UF. Okay, and this comes out to be 106.4 kilojoule per kilogram. Again, taking up all the values from table A11. So now we have enough information. We can go back and write the equation Qn as equal to MEHE plus M2U2 minus M1U1. We have everything that we can fill in here. So ME, as we have seen before, is equal to M1 minus M2. So M1 being 39.02 minus 4.706 times the enthalpy at the exit, which is 93.42, plus mass at state 2, 4.706 times internal energy at state 2, or UG, 243.78, minus mass again at state 1 here, so 39.02 times the internal energy at state 1, which is what we just calculated. So Qn would be 201.1 kilojoule, right? So this is the amount of energy that we will need to provide to the refrigerant, so that as the liquid is exiting the control volume, the pressure remains constant at 800 kilopascal. Now, if you think carefully about it, right, we said here, if you look at state 1, we said mass of the fluid or saturated liquid is 35.49 kilogram. Okay, and mass of saturated vapor was 3.529 kilogram. But at state 2, we realized that the mass at state 2 is 4.706 kilogram, right? And at state 2, we just have saturated vapor. So what we are saying is basically the mass of saturated vapor, which is simply the mass at state 2, is greater than mass of saturated vapor at state 1. And this simply tells you that, as you're providing heat into the system, some amount of liquid got converted to vapor. That's it, nothing else happened. And because this liquid got converted to vapor, as you were trying to keep the pressure constant, you did not have to remove that liquid anymore, right? So instead of removing all 35.49, we removed a slightly lower quantity because we just did not have 35.49 kilogram in terms of saturated liquid anymore. The amount of the mass in terms of saturated vapor had increased to 4.706 simply because we had to heat up the refrigerant. Okay, so this is a slightly complicated problem, right? It requires you to think carefully and look through it. And I encourage you to solve it on your own and get back to me in case of any questions. I'll be solving a similar problem, although that a problem that deals with ideal gases in the class tomorrow. Okay, so see you and have a nice day.